So this lesson is about standardized or what are sometimes called z-scores. A z-score pretty much always represents, a z is the letter that's used for standardized scores pretty much all the time. Let me give you where this might be used. What they are can be used for quite effectively is allow us to make apples to oranges comparisons. I'm going to take an example that's very much like one from the book. Okay, let's say we've got an adult male. This is all U.S. So we have adult male who is 6'5" tall guy. Now let's say we have an adult female who is 6 feet tall, exactly 6 feet 0 inches. Now the guy is taller than the girl, obviously, but the question we want to ask is which one is more unusual out of its set of out of the population it's drawn from. Is a 6'5" guy more remarkable amongst all guys than a 6 foot tall woman out of all women? And z-scores or standardized scores are a very effective way for making a comparison like that. Here's the idea behind them. What you need to know to make use of standardized scores is you need to know the mean and the standard deviation of the population. And I've looked these up online. So let me make a little table here that we can keep track of these things for. So we'll have guys, male and female. Then we'll put the mean. A letter that is often used for population mean is the Greek letter mu. Stands for, it's an M, it's a Greek M. And we'll have the standard deviation, and a letter that is often used for a population standard deviation is the Greek letter S. We'll see this pattern over and over in the course with the Greek letters being used for population values. So let's say the population mean, the mean of all men's heights is 69.7 inches. And that's with a standard deviation of 2.9 inches. This is what I looked up today. For women, the mean height is 64.3 inches with slightly smaller spread. The standard deviation is only 2.7 inches. So there's not quite as much variation among women's heights as there is among men's heights. So we need to know these in order to make use of the z-score. Okay? Here's the idea behind the z-score. What we're going to do is let's imagine putting all of men's heights on a number line. What we're going to do, however, is we're going to put the mean height, which is 69.7 inches up above, at the center, sort of the middle of the number line. This is typical. And then we're going to put tick marks down, but the tick marks are going to be exactly one standard deviation apart. So this is going to be 2.9 inches, 2.9 inches, 2.9 inches. And likewise here, 2.9, 2.9, 2.9. So if I add 2.9 to this, I'll get 71.6. Wait, is that right? No, 72.6. And then I'll get 75.5. And then I'll get 78.4. Likewise over here, if I subtract standard deviation, subtract 2.9, I get 66.8, and then I get 63.9, and then I get 61.0 inches. So these are all inches. So where is our 6'5" tall gentleman in this? Well, what is this in inches? This is 72 plus 5, or 77 inches. So 77 inches is pretty far up. 77 inches is someplace up here. 75.5, 78.4. So 77 would be, this would be about, so let's see, around here, I'd say. 77 inches is around here. What we can do is we can compute the z-score for this, or the standardized score for this. And all a standardized score is, so finally we have the definition. The standardized score or z-score is the number of standard deviations a value is above or below the mean. This is an extremely important idea, this idea of a standardized or a z-score. So if we look at this number line, we see this is 1 standard deviation, this is 2 standard deviations, this is 3 standard deviations. So right under here I could write z-scores. Okay? A value at the mean would have a z-score of 0. It is neither above nor below its population means, so its z-score would be 0. If you're 1 standard deviation above, your z-score is 1, and likewise 2 or 3. If you're below the mean, you have a negative z-score. So this value here, 66.8 inches, would have a z-score of -1. It's exactly 1 standard deviation below the population mean. This would have a z-score of -2. This would have a z-score of -3. And the way we compute a z-score is we simply see how far a value is above the mean, and then we divide that by the standard deviation, which will tell us how many standard deviations is above the mean. I can write this down as a formula. It's often called the z-score formula. What you do to get the z for some value you want to know about, you take the value and you subtract from it the mean. That will tell you how far it is above the mean. So this would be 70, oops, can't see that. This would be 77 minus 69.7. So I would take that difference. So that would be the inches above the mean. But then I want to know how many standard deviations that is, so I would divide it by the standard deviation. So if this difference was 2 standard deviations, divided by the standard deviation, I would get a score of 2. So let's compute the z-score for 77 inches up here. So the z for 77 is 77 minus the mean, 69.7, divided by the standard deviation of 2.9. And I get up my calculator.
77 minus 69.7. So he's 7.3 inches above average. And if I divide that by 2.9 inches, I find that his z-score is 2.52 approximately. Usually z-scores are written to 2 or 3 places past the decimal point. So my arrow is a little bit misplaced up here. My arrow is just a bit, it probably should be over here, so let's fix that. It's just right above 2.5. So that 77 inches is 2.52 standard deviations above the mean. So that's a tall guy. 2.5 standard deviations, as we'll learn later, is pretty remarkable. How can we use this to make comparisons? Well, the way we use it to make comparisons is, let's look back at our adult female. Our adult female was 6 inches tall, which is, of course, or 6 feet tall, 6 inches. 6 feet tall, which is, of course, 72 inches. So now what I'll do is I'll compute the z-score for this adult female using the population mean and the population standard deviation that I looked up earlier. So let's do that. So a z for a 72 inch tall woman, 72 minus the mean was 64.3 inches. These are actually all inches if we want to be precise,
divided by 2.7 inches. And if I use my calculator again, let me pop it up over here. 72 minus 64.3. I could probably do this in my head. I just don't want to think about it. So this woman is 7.7 inches above the population mean. Dividing that by 2.7 inches gives me a z-score of 2.85. And notice, as an aside, z-scores are unitless. This is inches over inches, so this is a pure number. Z-scores don't have a unit. So we find that this woman's height is 2.85 standard deviations above the mean. And so we would say, as compared to the guy's standard deviation was only 2.52 standard deviations above average. We could say an interpretation of this as is a 72-inch tall woman is more unusual, more remarkable than a 77-inch tall man. Because the woman's height is 2.85 standard deviations above the mean. The guy's height was only 2.5 approximately standard deviations above the mean. This is one way to use z-scores. So one more quick example, and then we'll relate them to what's called the normal distribution in the next part of the lesson. So, and one last example. Let's use the women's mean and standard deviation from up above. So, mean for women, using that Greek letter mu again. Mean for women was 64.3 inches, and we'll use standard deviation for women. It's 2.7 inches. Using those values from before. That's the Greek letter M, that's the Greek letter S, mu and sigma. Let's say I ask the question, what is the height of a woman with z-score equal to negative 0.6? So it's turning it around the other way. I'm giving you the z-score, telling you the z-score is negative 0.6, and I want to know, given this information, how tall is she actually? So this is hopefully straightforward. Remember that this is telling us how many standard deviations the value is above or below the mean. So we know the mean. The mean is 64.3. And then we know that her height is 0.6 standard deviations below average, below the mean. So I'm going to subtract from this 0.6 times the standard deviation. So there's the standard deviation, there's the mean. And this will tell me her actual height. And again, I'll get my calculator. I don't want to have to do all this arithmetic in my head. So I'm going to do 64.3 minus 0.6 times 2.7. And we see that she's 62.68, or about 62, approximately 62.7 inches tall. So that would be 5 feet, 2.7 inches. So that is an introduction to standardized scores. They're very important, and thankfully I hope you'll agree they're not too complicated.